Hi everyone, welcome to today's lecture on signal processing and matched filtering, or how to find signals in noisy data when you have a template for what your signal looks like. I'm Maya Fishback and I'm a postdoc at Sierra at Northwestern University, and I'll be giving this lecture. So in today's lecture, we'll discuss firstly the introduction to the problem, and my background is in gravitational wave astronomy, so I'll be talking about this problem from the perspective of detecting gravitational wave signals with LIGO and Virgo, but I hope that the techniques we will learn today will be applicable for other time series data that you may encounter in your own research. Second, we'll get into these methods. So we'll talk about the detector noise. And third, the signal templates. Fourth, how to actually calculate the matched filter signal to noise ratio. And fifth, how to evaluate the statistical significance of a trigger. And I will define all of these terms as we go along. So first, we'll be talking about LIGO time series data. Again, this is just an introduction to the kinds of problems that we have in detecting gravitational wave signals. So in LIGO, the time series data is strain versus time. And LIGO, for those who are not familiar, is one gravitational wave detector in this worldwide network of gravitational wave interferometers. LIGO actually refers to two detectors. There's one in Hanford and one in Livingston. There's also a third gravitational wave detector in Italy called Virgo. There's a Japanese detector called Kagra, which will join the network soon. And LIGO India is currently under construction and it will hopefully be operational later this decade. So all of these interferometers are there listening to gravitational waves from the universe. In particular, some really good sources of gravitational wave signals include black holes and neutron stars in binaries that actually merge. So here is a little movie that shows some of the signals that have been detected so far. There are more than 50 of these in the latest catalog from the LIGO and Virgo collaboration. And you can see each one of these systems are these two compact objects that are spiraling around each other and eventually collide. And here's what one of these collisions looks like in terms of the emitted gravitational waves, which are these ripples that emanate from this merger outwards into the universe and propagate into the universe, and some of them eventually reach the Earth. And the way they're detected is through laser interferometry. So what the gravitational waves are actually doing are stretching and squeezing space-time itself. So distances are changing when a gravitational wave passes through. And that gets measured by this interferometer. So you have these lasers, two arms, and the laser light travels through the two arms. And when a gravitational wave passes through, the distances between the arms are changing. Here you can see how that laser light is a wave and it travels down each arm, reflects off the mirrors. The mirrors are the test masses at the end of the arms, then recombines and goes into this output here. And when the relative distance between the two arms has changed, light takes a little bit longer to travel down the longer arm, and it creates this interference pattern at the output. And that is what these detectors are looking for, the specific pattern of interference that corresponds to the pattern at which the relative length of the detector arms are changing. And so gravitational wave signal from these merging compact objects that we've been detecting are described as following. So, right, these detectors are detecting this gravitational wave strain, which describes how much space-time is stretching and squeezing. And this amount of stretching is the strain as a function of time, and it's this wave. And the early part of the wave, it's this in-spiral process. So the gravitational wave signal, the frequency depends on the frequency that these two black holes are in-spiraling around each other. Black holes can also be neutron stars, right? And as they get closer and closer together, the frequency increases. And you can see that here in this example waveform. Then there's a merger where the gravitational wave signal peaks, and when you have a final black hole, it rings down, and then the signal dies out and there's no more gravitational waves. So this is this form of frequency as a function of time. We can see it's called chirp because the frequency is increasing with time, and we can actually listen to that here. Yeah, so you heard that chirp against the rumble of the background noise, and that chirp is the kind of signal that we are looking for in this very noisy data. So here I'm just showing the abstract from the paper announcing the first ever observation of gravitational waves. This paper came out in 2016, and it reported on this source that was detected on September of 2015. And here I've just highlighted the things we'll discuss in this lecture. So in particular, the matched filter signal to noise ratio, and then how to go from that to a false alarm rate and a significance statement. And by the way, if you want more background about any of this, I think that this paper is actually a very good and a pretty good introduction level to some of these techniques also. It's a very well-written paper, and I joined the LIGO collaboration after this paper was written, so I'm not biased. I'm not one of the authors. Okay, so that was a very quick introduction to the gravitational wave detection problem. If you want more background material, again, check out that paper that in the abstract that I showed. But now going on to discussing some of the math behind all of this. So first, we have to understand what the detector noise is. And in the for the purpose of detecting signals, we assume some properties about the detector noise, as I'll describe here. So in the absence of a signal, just a notation, the detector output is a noise time series, which I'll write as n of t. And we often approximate the detector noise as being stationary, which means that the autocorrelation function of the noise, which is defined as this expectation value of the noise at some time t times the noise at some other time t prime, depends only on the difference between those two times, t minus t prime. And because the detector noise is stationary, only depends on the properties, only depend on the difference between two times, this motivates us to do the analysis in the frequency domain. So we take a lot of Fourier transforms. For stationary noise, what this means is this property means that the noise in each frequency bin is independent of the other frequencies. Additionally, the noise is often approximated as being Gaussian, which means that at each frequency, the noise follows a Gaussian distribution. And that Gaussian distribution is described by the power spectral density or the amplitude spectral density. And that's abbreviated as PSD or ASD. And just as an aside, both of these, so stationary and Gaussian, are properties that are only approximations to the real detector noise. And as we'll see later, to calculate the actual statistical significance, the noise background has to be estimated empirically, because in reality, it's not as well behaved as these approximations, but these approximations are good enough to use in searching for gravitational waves. So a little bit more about stationary and Gaussian noise. We work with discrete samples from the time series data in real life, right? We always take discrete samples. For signal searches in gravitational wave data, the sampling frequency is around 16 kilohertz. And so when we take samples from this noise time series, NFT, we have these discrete samples, Ni, which are sampled at times Ti, that make up this vector. And we describe the noise as a stochastic process. So these Ni follow some probability distribution, which is described as P of N, where N here, right, is the vector consisting of all the Ni's. In Gaussian noise, this probability distribution is a multivariate Gaussian. So it's specified by a mean and a covariance. And again, in stationary noise, the covariance matrix, here C, depends only on the time lag. So the difference between 2 times Ti minus Tj, the absolute value of that. And so we can characterize this covariance matrix by just a function of the time lag, C of tau. So in the frequency domain, things are pretty simple. If when we apply the Fourier transform to a stationary time series, the covariance matrix between two frequencies, Fi and Fj, is diagonal. So here, this defines, we can write this in terms of this Sn of Fi function. And this is just saying that the noise is uncorrelated between the frequency bins, which we said earlier. And at each frequency, we have this function S of n of that frequency, which is just the Fourier transform of the correlation function. And it's the power, it's called the power spectral density, or PSD. We will talk about this PSD a lot throughout this lecture and throughout the corresponding tutorial. The amplitude spectral density, which is another term that comes up, is just the square root of the power spectral density. So it's the same as standard deviation is to variance, right? And for white noise, sometimes when you do these time series analyses, you encounter the term white noise. That refers to when the power spectral density is flat. So it's the same at all frequencies. For gravitational wave detectors, this is generally not the case. The noise is stationary and it's Gaussian, but it's not white, meaning the noise at different frequencies is different, has a different variance in different frequency bins. So we can see that here, actually. Here is an example of an amplitude spectral density. This is from this paper, which you can check out. It goes into really all the details of doing gravitational wave data analysis with LIGO and Virgo and what is being done. So you can see often you see this plot in log space. You can see at low frequencies, this ASD is much higher, so there's more noise at lower frequencies. There's, again, more noise at the highest frequencies, and you'll be playing around with this in the tutorial as well. So just a little bit more about how we handle the noise and do this Fourier domain analysis of the data. So again, the key here is just to Fourier transform everything. It's much easier in the frequency domain when you have stationary noise. And what we do is we take that data stream and apply this discrete Fourier transform, typically a fast Fourier transform or an FFT to go from the time domain data to the frequency domain data. And to do that, we have to, there's the highest frequency we can resolve with the data, right? So if you want to resolve some frequency, you have to make sure that you're sampling at sufficiently high frequency. So for a given sampling frequency, you can only resolve frequencies up to half of that sampling frequencies. That maximum frequency you can resolve from your time series data is the Nyquist frequency. That's just what it is called. If the data contains frequencies higher than twice the sampling frequency or the Nyquist frequency, we need to apply a low pass filter to that data to blur the higher frequencies. Meanwhile, the spacing between two frequency bends gives you the inverse of the signal duration, or if you've sampled for some time, say 500 seconds, that total duration determines the spacing between the two frequency bends that you can resolve, right? That'll be 1 divided by 500 hertz. And given discrete samples from a time series, the sampling frequency and the signal duration determine the frequency bends. So this just gives some background on how to go from your discrete samples in the time domain to samples in the frequency domain. Okay, so that was some background about detector noise, what it means to be stationary and Gaussian, and some brief review of taking Fourier transforms and working in the frequency domain. Now, in the next bit, I'll just talk about what the signal templates are. And I haven't really defined this, this word templates yet, but I will soon. So we looked at this before, but the gravitational waves from merging black holes, also neutron stars, follows this specific chirp-like waveform, right? So there's this specific form for the signal, no matter what masses the black holes are, how fast they're spinning, it always looks kind of like this chirp. So it starts off at low frequency, then the frequency increases, and finally there's a merger and this quick damping in the ring down. So essentially this waveform, this chirp, is what we're looking for in the data. And we know what we're looking for, which is the key thing behind this whole matched filter. And we'll discuss this a little bit later, but basically we can construct a template bank. So each template is essentially a model for what the gravitational waveform will look like for a signal with some parameters. Here, the parameters are the primary mass, M1, the mass of the bigger black hole, and the secondary mass, M2, the mass of the smaller black hole or neutron star. For the purpose of this talk, neutron stars are just low mass black holes. So you can see here that this is an example of a template bank, which just means that each one of these points, we have calculated what the waveform should look like. So as we go to higher masses, the waveform will move to lower frequency. At lower masses, it's higher frequency. The mass ratio also affects what the waveform looks like. But essentially, we've calculated something that looks like this at each point in this parameter space. And these are our templates. Now, in the next bit, I'll talk about how to go from understanding your noise, more or less, and having these templates to the crux of the calculation, which is the matched filter signal to noise ratio, or SNR. I'm sorry for people who have seen other abbreviations for signal to noise ratio in the gravitational wave community. It's always abbreviated SNR. So in this talk, SNR means signal to noise ratio, not supernova remnant. So here is a movie that I'll come back to later once we go through all the details of the calculation. But this gives an idea of the big picture. So the complete picture behind this matched filter process. And the idea is that we have our noise, we have our data stream. H of t is the gravitational wave strain as a function of time. Here you can see that in this background pink, it looks like this forest of lines, but it's actually this curve that is the strain as a function of time. And there might be a signal embedded in this, and the signal will look something like this. And what we do is we slide these templates effectively over the data. And let's play that again. We're going to slide a template over the data, and you'll see that as a function of how much we've slid the template, we calculate this signal to noise ratio, which here is denoted by rho. And that gives us another time series, which is the matched filter signal to noise ratio as a function of the time lag. So we're sliding the template over, and the time lag between the signal and the template is this time variable here. And you can see we're going to slide a template over this noisy data stream and just watch what happens to this signal to noise ratio as a function of time. And we're sliding. Here, the signal perfectly lines up, or the template perfectly lines up with the signal, and we get this spike in the SNR time series. And that spike is our trigger. So really what we do, we slide these templates, and there are many templates in the bank that are being slid over gravitational wave data. Sometimes there's a signal, and we get this peak in the time series. There's some threshold that we pick, and some threshold in SNR, and the peaks that lie above this threshold at a higher SNR are saved to disk, right? Those are the triggers. That's what we mean by triggers. Some of them may be very high significance, and we think they're astrophysical, and some of them may be low significance, and at the very end of the talk, we'll go over how to calculate that significance. But for now, these peaks are just the triggers. Okay, so we already introduced some notation. Here's a little bit more notation. And so our data stream, as we saw, is denoted as H of t. This is strain as a function of time. We have some noise time series, which is N of t, and this signal, which may potentially be in this data stream, and the signal is denoted as S of t. And then we also have these templates in this template bank, which are also this time series t, big T as a function of little t, and lambda, where lambda are the parameters describing the templates, like the masses and the spins of the black holes at which we've calculated a template waveform. So the data stream H of t is N of t, the noise, plus S of t, the signal, if there's a signal there. So for detecting gravitational waves, does this mean that S of t has to be larger than N of t, the noise, so you can tell that there's a signal over the noise? And thankfully, that we do not need this criteria. Thankfully, as you saw in the movie, S of t, the signal, can be much smaller amplitude than the noise. And this is the power of matched filtering, is that we can detect signals that are buried in the noise because of this matched filter. Okay, so how do we calculate the matched filter SNR? And the next few slides will have quite a bit of math on them. I will try to go through it carefully and slowly, but feel free to pause and write down the equations and work through them yourself if you're so inclined. So the basic idea is that we correlate our data stream h of t with templates t to find the signal s of t. Again, this is what you saw in that movie. Here, the template t is the filter. So going back a step, for any filter, here k, you can correlate the data stream and define this statistic h hat for your data stream h of t, which is just the integral of h of t times your filter k of t integrated over all times. The value for this statistic you've defined by doing this correlation. So the value of h hat over different noise realizations follows some statistical distribution. And the signal to noise ratio is then defined as the ratio between S, or the expectation value of h hat when there is a signal, and N, which is the root mean square or RMS value of h hat when there is no signal presence. So these words, expectation value and RMS, are referring to averaging over noise realizations. So basically h hat is drawn from a statistical distribution depending on the noise realizations, which is a random process that we described in the first part of the talk. So let's start with calculating the S in the signal to noise ratio, which is this expectation value of h hat. You can see we just rewrote the definition for h hat here. Now k of t is just our filter. That's a constant in different noise realizations, but h of t, we want to take the average of that over different noise realizations. We expand h of t as s of t plus n of t. Again, s of t is our signal. That's the same regardless of noise realization, but we can take the expectation value of n of t over different noise realizations. But because we have Gaussian noise, this expectation value is just a constant, right, which we can take to be 0 if there's some offset just subtracted beforehand. So this whole term goes to 0, and our S term, the numerator of the signal to noise ratio, is just this integral here, which we can write, this integral is over time, but we can write it as being an integral over frequency, and this relation is just a property of Fourier transforms. So the S part is given by this integral over all positive and negative frequencies here between the Fourier transform of our signal and the Fourier transform, the complex conjugate of the Fourier transform of our template. Here the star refers to complex conjugate throughout this talk. Okay, now let's turn to the N term in the signal to noise ratio. So the N term is the root mean square, or this h hat statistic squared, the expectation value of that, minus the square of the expectation value of h hat for S equals 0, so no signal, or in the absence of a signal, right? S here's the signal. So we can, this is just the definition of n squared, and here we can write this out as this term just goes here, but now we're writing h hat of t in terms of, again, this s of t plus n of t. Both of these terms are 0, right? Because in these, we've assumed that there's no signal. So this first term goes to 0 as s is 0. And we've said that the expectation value of n of t is also 0. So we can get rid of this whole term and the big parentheses, and we have n squared equals just the expectation value of h squared of t under the assumption of zero signal. And we can write this out as this integral here, where we were again using the definition of h hat. And we can apply a Fourier transform to this thing, and let's apply a Fourier transform to this n of t times n of t prime, the expectation value over different noise realizations. And this is just the definition of a Fourier transform. So we've written it in terms of the frequency domain noise. And remember that we defined the power spectral density to be essentially this term here. So the power for the assumption of stationary Gaussian noise, the expectation value in this term here is defined in terms of this power spectral density. So there's this delta function because the variance is, or the properties of the noise are independent between different frequency bins. And this S sub n of f is the power spectral density. So we can then write n squared here, which again is just this term, in terms of the absolute value of the Fourier transform of the template k times the noise power spectral density at some frequency. So putting everything together, for any filter k, the matched filter signal to noise ratio is the S term divided by the N term, which is given by this expression here. And we can understand this expression a little more, which I'll go through in this slide. And now the question we want to answer from this expression here is what template should we be using? What's the optimal signal to noise ratio? What's the maximum this SNR can be? And what filter or template can we use to give us that maximum signal to noise ratio? So we can define an inner product between any two time series A of t and B of t, and this inner product notation will help us understand this formula. So let's define this inner product between A and B, two time series, as the real part of this integral here. So the complex conjugate of A in the frequency domain times B in the frequency domain divided by 1/2 of the noise power spectral density as a function of F. This is because these are real time series, we get factor of 2 from here, and we get another factor of 2 from switching the integral bounds from -infinity to infinity to 0 to infinity. And we can just write this as 4 times the real part of the same thing without the 1/2 term and switching the bounds of the integration. Okay, so if we define for any filter k, we define this u function, which is just k times the power spectral density times 1/2. We can write s divided by n, or the SNR, as this term. So we just went from this equation here, using the inner product notation. It's the inner product between u and s, our signal, divided by the inner product between u and itself, the square root of that. So from this inner product notation, it's easier to understand this fact, which is that the SNR is maximized when we take U, which again just depends on our filter and the power spectral density of our noise. We take this U to be parallel to the signal S, so proportional to that signal itself. So basically the optimal filter to use, the optimal filter K, is proportional to the signal itself weighted by the power spectral density S sub n. So if we take that optimal filter, which is here written in math, what this sentence above says in words, then the optimal SNR for any signal will be given by this equation, where this little s is the signal, this S sub n is the power spectral density. So this is our optimal SNR, and the optimal filter we want to use is basically the signal we're looking for itself. So how do we actually get that? Let's say we have a filter, we have a template in our template bank that matches the signal that is embedded in our data. How do we find it? Well, when we do a search, we don't know what the exact signal S is or when it occurs. All we have is our data stream, H of t, so again, strain as a function of time, and our template bank, which consists of these templates, big T, as a function of time, and different lambda denoting these different templates. So as we remember from the movie, we're essentially sliding the templates over the data, and we want to calculate this SNR as a function of the time shift between each template and the data, or how much we've slid it. A spike in this time series is a trigger, as I described before, and these triggers are the potential signals of interest. So luckily, this calculation is actually pretty straightforward if you do it in the frequency domain. So instead of taking your different time shifts and for every time shift calculating the SNR according to the formulas on the previous two slides, we can get all the possible time shifts at once by just taking a single fast Fourier transform, or FFT. So how this works, and you'll practice doing this yourself in the tutorial, is the following. So what we want to do is calculate this SNR between our template T. So before in the formulas, we had a general template given by K. Here I'm using templates for our template bank, so the Ks are now Ts. We have our template, and we want to calculate this SNR, where here I've written it in this inner product notation. So it's the inner product between T and our data stream H, normalized by the inner product of T and itself. And here I've written this as a function of tau, where tau is the time shift between the template and the data H. So the template itself is really a function of that time shift. So you can think of tau as being one parameter of this template, which perhaps represents the time of merger. We don't know. We can look at different masses that describe the waveform, and we can look at different merger times when in our detector did the signal merge. Now we can see that it makes things a lot simpler when we consider Fourier transforms, because if we write T tilde of F in the frequency domain, which is the Fourier transform of T at some fixed time tau prime of 0, then the Fourier transform of T at some different time, T prime equals to tau, is just the Fourier transform of t times e to the I 2 pi f times tau. And so we can write this numerator here, the inner product of t with h, as just this, right? We can just, using the definition of inner product, we can write it as the following in the frequency domain. But this is just the inverse Fourier transform of this equation here, just the inverse Fourier transform of t in the frequency domain, complex conjugate of that, times your data stream, the Fourier transform of that in the frequency domain, divided by the noise power spectral density S sub n at that frequency. So if we can compute this, if we can take the Fourier transform of everything, work in the frequency domain and compute this, and then take the inverse FFT, this gives us the time series. This actually gives us something that's proportional to the SNR time series, because this here neglects this normalization term in the denominator. But for finding peaks in the SNR time series, this is good enough. All we have to do is compute this, compute this. This is just for our template, our data stream, and the noise power spectral density that describes our data. And from that, we can take the inverse Fourier transform, which we can do as an inverse FFT, get the time series SNR as a function of the time lag tau, and easily find this tau, this time shift that corresponds to a local maximum. And if it's above some threshold, that is our trigger. So again, now that we've seen all of the math behind it, let's just go back to this movie, which illustrates here. So in this case, we have this, our data stream, h of t, is this pink curve in the background, embedded in which is a signal, s of t. If we didn't explicitly draw the signal on top of this time series, just from looking at the pink, which is our data, we would have no idea that it's there. But we have these templates. One of the templates that we're sliding over matches this signal well, and that's the template that we're going to see slide over. And here is our SNR time series, and you can see that it spikes when the template is over the signal. So when we have the right time lag, we can find this trigger and identify it in this way. Okay, so how do we actually construct the template bank? It seems like we maybe just have to be lucky and have a template that matches the signal we're looking for. Well, as you may remember from the image of the template bank, we want to place these dots densely enough so that at any signal from some real M1 and M2, from some real pair of black holes with these masses, we want the overlap between the template and the signal to be close. And what do we mean by close? What we mean is that we want the signal to noise ratio loss that we lose due to the fact that we can't possibly cover every combination of signal parameters in the universe. We want to limit that SNR loss so that we don't lose too many events. So when we have some templates denoted by their different parameters, lambda, and again, this lambda can be the M1 and the M2, it also is the spins of the black holes. We have these templates, and the maximum signal to noise ratio that we get over all those templates in the bank, we can write that in terms of this, which is just the definition of the signal to noise ratio between our data stream S and our template. The maximum of this over the bank here we're just multiplying by a constant, same in the numerator and the denominator. And we're just moving one of these factors of the inner product between s and itself and the square root of that into the denominator here. And the reason we do that is because then we get this term here, which is the optimal SNR. So this is the signal to noise ratio we had for if the template was the signal itself. And this first term here then represents the factor by which we've degraded the SNR due to the discreteness of the bank. The fact that T of lambda is not exactly the same as S. And so this term here is called the fitting factor. In real gravitational wave searches with LIGO and Virgo, we typically pick this fitting factor to be no less than 0.97. And that translates to a loss of events of around 10%. So if you say I'm willing to lose 10% of my events due to the discreteness of the template bank, of course, we can't have an infinitely dense template bank, and then we would want this fitting factor to be around 0.97. And you can see that by this simple math here. Just the rate of detections is proportional to the sensitive volume, so how much of the universe can we probe, which is proportional to the distance, how far away can we see a source, the cube of that. And the distance scales inversely with the signal to noise ratio. So distance cubed is proportional to SNR to the -3. And if the SNR over our bank, the maximum signal to noise ratio we can get with our templates is 0.97 of the ideal case, then the ratio of the rate that we get with our template bank over the ideal case is around 0.97 cubed, which is around 90%. So that's where this fitting factor of 0.97 comes from. So we've now talked about almost everything. We know how to find triggers using our template bank. We know how to construct a template bank, or at least what fitting factor we want for our template bank and what that means. The final thing we have to know how to do is to actually calculate the statistical significance of a trigger. Once we've found that spike in our SNR time series and we know that there is something interesting there, how can we tell whether it's actually statistically significant or not? So what we do is assign some ranking statistic to these triggers, which is usually something like the matched filter signal to noise ratio itself. So we know that we've picked triggers because they have a high signal to noise ratio. So the higher the signal to noise ratio, usually the more significant the trigger is. So we have this ranking statistic, and the question we want to ask is how often can noise produce a trigger of a similar or higher ranking statistic? And to answer this question, for calculating the optimal signal to noise ratio and everything, we've just assumed that our noise is stationary and Gaussian. But if you want to actually calculate the statistical significance of triggers, you have to take into account that the deviations from the noise background from stationary and Gaussian noise. We have to determine the noise background empirically. And this is challenging because we can't turn off the universe, turn off gravitational waves, and collect just noise. And furthermore, we only have a finite observing time. So even if we could turn off the universe and know that we're analyzing just detector noise, if we've only observed for 2 years, the most we can ever say is that noise doesn't produce something so significant once every 2 years, which is not very significant. So what's actually done is to determine the background noise distribution using time slides. So the data between two detectors, for example, LIGO Hanford and LIGO Livingston, is shifted by 0.1 seconds, which is greater than the 10 millisecond intersite propagation time. So as long as you shift the data by more than 10 milliseconds, you know that there are no coincident gravitational wave signals in your data. Any coincident triggers between those two data sets are definitely noise, not gravitational waves, because gravitational waves would not be able to appear at the same time in that time-shifted data between the two detectors. So that's how the noise background is estimated. And you can see here, you then get a curve, you then run your search in that noise background, and you can do many different time shifts to build up enough statistics and essentially create a Hubble time of noise background distribution empirically using the time slides. So that gives us this distribution here, and this is just a histogram, so number of events as a function at these different detection statistics, which again is something similar to the matched filter SNR. And here in black is the search background that we get doing the time slides. And this is from the very first observing run of LIGO and Virgo. You can see here in orange are everything that was found as a trigger. So you can see that there are 3 events here that are pretty separated from the background, especially the loudest event, which was also happened to be the first detection, GW 150914. At this detection statistic of more than 22, there is essentially no noise background. And that is the same thing for this event and also sort of for this event. And you can actually see there are 2 different noise background distributions here. One is calculated from these time slides, just directly using the real data and doing the time slides between the detectors. And one is calculated from the time slides, excluding the chunk of data corresponding to when this signal appeared. And the reason you see this difference is that when this gravitational wave signal is really in the data, even when we do the time slides, it sometimes rings up against some noise in the other detector just because it's so loud. Sometimes we get a pretty high detection statistic just from this real signal lining up with some noise in the other detector. And so if you are really looking to just measure your noise, you can exclude this signal because it definitely doesn't occur by noise and get this other distribution here. And you can see here on the top axis, we can assign this how significant this separation between the noise background and the event is. And the way that's done is by computing this false alarm rate, which is, again, it's this frequentist way of calculating significance. So we have a null hypothesis, which is that the data set has no gravitational wave signal. And the false alarm rate is if the null hypothesis is true, the rate at which our detectors would produce a noise trigger of equal to or higher ranking statistics. is this false alarm rate. The units of that is 1 divided by time. So it can be like 1 divided by 2 years for pretty quiet signals, or like 1 in a Hubble time for the loudest events. And to go from this false alarm rate to a false alarm probability, we just multiply that false alarm rate by how long we've been observing. So if we've been observing for a year and the false alarm rate is only 1 per year, the false alarm probability is 100%. It's actually quite high, right? And we can then go from that false alarm probability to these 1 sigma, 2 sigma, 5 sigma significance statements by just assuming this Gaussian distribution. So that is all that those standard deviations, significance things mean on a plot like this. Okay, so to conclude, so hopefully now that you've seen this entire lecture, you know a little bit more about what it means to detect gravitational waves with LIGO and Virgo, how the detector noise is characterized as being stationary and Gaussian, what terms like the amplitude spectral density and the power spectral density mean for stationary and Gaussian noise, how to correlate our data stream with templates from this template bank and what those templates look like, and how to calculate our signal to noise ratio with matched filtering, what the optimal signal to noise ratio is, how to get a signal to noise ratio time series and identify triggers, and then finally, once you have those triggers, how to estimate the statistical significance and have a false alarm rate and a false alarm probability, and be confident that you've actually detected something that is not your noise distribution. That's the end of today's lecture, and I'll see you in the session in a couple of weeks.